Hello, everybody. This is Mike Human from G2M Research, and welcome to our webinar. Today, our topic is, can your servers handle the size of your SSDs? Let's jump right in. First, I'll go through the ground rules, and each of the sponsoring vendors will provide a short presentation on the subject. Then we'll have some key questions. We have 3 questions. We'll ask them in a panel format. We'll also have 2 audience surveys in between those questions. Finally, about a 7-minute audience Q&A, and then we'll wrap up. This webinar is being recorded, and we'll make that recording available to everybody who registered for the webinar. Those will be sent out roughly 2 days after the webinar, along with a PDF of the slide set. If you have questions, please use the Zoom Q&A window. We're not going to answer the questions as we go through things. We'll hold them to the end, but please put your questions in, and then we'll address them when we get to the Q&A section. So with us, our panelists today are Matt Hallberg. Matt is the Senior Product Marketing Manager at Kioxia. We have John Michael Hans, who's the Senior Strategic Planner and Product Manager at Intel on the SSD line, and Josh Goldenhar, VP of Product Marketing at Lightbits Labs. And again, I'm Mike Hume. I'm the Managing Partner at G2M Research. So it's been funny because if you've looked at the news regarding storage over the past couple of years, one of the subjects you see pop up is, are SSDs too big for servers? If you look at it, SSDs that continue to increase in capacity, pretty much with Moore's law. They keep doubling about every 1.5 to 2 years. Servers, on the other hand, have somewhat plateaued, and clock speeds and feature size improvement rates have slowed quite a bit compared to what they were, say, 10 or 15 years ago. If you look at 5 years ago, you could have 6 SSDs into a single server, and that would be pretty common. Simply from a capacity standpoint, one SSD can probably handle the workload of most servers today. And obviously, that potentially causes issues as far as redundancy, data sharing, data management, and other subjects like that. So one of the things we're going to talk about today is how do you balance those relationships? There's been several different approaches that have been proposed over the past few years. Networked SSDs shareable over Ethernet or other sorts of interfaces is one approach. Scale-out flash storage software is another, where you actually group all the SSDs together and make them look like one namespace. And then smart storage and computational storage. So, we've got panelists who can talk to at least 2 of those subjects and maybe all 3. And, what we're going to talk about in this webinar is what are the trade-offs of these different approaches? How do you handle data management? Do these make bigger issues in network congestion? And we'll explore all those topics today. So hopefully everybody will enjoy this session. And with that, it's not Joel, sorry. It's Matt Hallberg. Matt, why don't you go ahead and take over?
All right. Hi, everybody. So today I'm going to be looking at this from the point of view of an SSD, what SSDs can do for failure mitigation, blast radius, etc. And there are 2 different things, 2 different approaches. So one of them is what's covered by the NVMe and PCIe specification. We'll be talking about asynchronous events and smart health logs, and then features unique to our product, the Kioxia CM6 and CD6. So I'll go ahead and go to the next slide here. Eventually. All right. So on the SSD side, we're going to talk first about asynchronous events. These have been defined in a PCIe well, it's been in the PCI spec for a while. And then for NVMe, I'm looking at the 1.4 spec. The specific version is 1.4 from 2019 to June 10th. It was ratified. So essentially, asynchronous events are used to notify the host of status, errors, and health information. And when an asynchronous event occurs, essentially the device or the controller or NVMe subsystem will notify what kind of event occurred. And there are a lot more different kinds of events, but some of them I'm just going to exclude because they're not relating to blast radius and failure mitigation. But there's things like invalid doorbell rights, diagnostic failures, which includes like a device self-test, a persistent internal error, which basically tells the host that they should perform a reset at their next convenience, and a transient internal error. So something happened, came and gone, but you don't have to reset. And there are other events like if they're firmware loading or some that were reserved for vendor unique. On the smart health status events, there's an NVMe subsystem reliability. Subsystem, I tend to just say is the SSD itself. Reliability of the SSD has been compromised. That could be due to significant media, i.e. NAND errors, an internal error on the SSD itself, if the drive has gone into read-only mode, or if the volatile memory backup device is failing. Volatile memory backup device being PLPs, power loss protection, supercaps, or polytantalum capacitors, or whatever fancy exotic stuff is out there. There's one for temperature threshold, spare below threshold, and we'll talk about this in the slide afterwards, but essentially the available spare capacity has fallen below a defined threshold. And there are others like notice event, command send event, vendor specific event. And essentially what happens is the device is going to keep bugging the host that an asynchronous event has occurred until the host takes necessary steps to clear the event. So these AERs, for anyone who has a child, it's, they keep bugging you. Daddy, I want something. Daddy, I want something. Daddy, I want something, until you eventually say, what do you want? Oh, I want a sandwich. Okay, I'll go make you a sandwich. Now leave me alone. Maybe not that harsh, but essentially that's what an AER is. There's these other things called like doorbell registers, etc. You go to the next slide. Oh, geez, do this today. Okay. On the smart health logs, so smart health logs have been around for quite a long time. My history goes back as far as SATA, early SATA, and I remember smart being around then. These are health logs that are used to provide general health information to the host, which works its way up through the software layer and is provided over the life of the SSD. So in NVMe, you would issue a git log page, which is log 02 hex. And I'm just listing out the relevant bytes because the blog page itself is actually rather large. So on the critical error side, that's byte 00, you have several bits that describe what the critical error is. Available spare capacity has fallen below threshold, which I mentioned in the previous slide, meaning the spare area that you had in the SSD has been used up and the drive can no longer be written to. Bit 1 is the drive has reached a temperature lesser or greater than a defined minimum or maximum threshold. So that's like if you have a cooling issue where a couple of your fans die, if the SSD gets too hot, it's going to prematurely age the flash inside. And so many SSDs, if not all SSDs, have failure mechanisms that essentially the drive says, oh gosh, I'm getting too hot. I'm going to, slow down my performance, or I'm going to turn the NAND off and wait until my temperature reaches a normal threshold. Normal as in normal operating threshold. Bit 2 is reliability has been compromised due to significant media errors. You would probably see this if the drive is, very well worn and used. As the drive gets older and older, the NAND itself, and this is true for just about all SSDs, not just Kioxia, but the NAND itself gets sort of crusty and overwritten, and you're going to get notifications that some of these NAND die blocks need to be retired, etc. The bit 3 is the device has been placed in a read-only mode. That generally occurs if there's no longer any area for the drive to write to. It's out of OP, it's out of spare area. And in read-only mode, you're able to go in and get all the data off of the drive. One of the cool things for us is, in most cases, we're still going to allow writes, albeit at a very, very tiny really bad performance, but that's to allow you to like boot up into Windows when there are reads and writes, and if you don't allow writes, the OS won't let you in. And last is the volatile memory backup device. Again, PLP capacitors have bad health or are failing, and that shouldn't happen during the lifetime of the SSDs. SSD PLP caps have come a long time since the 90s and early 2000s, when you would have PLPs that would die within 2 or 3 years. Nowadays, these PLPs, these super caps, et cetera, are rated for 10 years plus. And all of us SSD manufacturers making enterprise and data center drives have done quite a bit of extensive research on making sure our super caps or whatever solution we're using don't die early. Otherwise, there's available spare area, which contains a normalized percentage of the remaining spare capacity. So you'll know like, okay, well, I have 10% useful life left of the drive. It's probably time for me to start looking at getting a replacement. There's available spare threshold. And this is a field settable item where you could tell the drive, don't tell me that the drive is ready to die until there's 5% life left, or tell me there's 10% life left, or tell me there's 3% life left. And what's going to happen is you're going to get an AER and a smart event that basically says, hey, we met this threshold. You wanted us to remind you that 3% of the drive left is left. You know, go do what you need to do to replace it. There's percentage used, which I mentioned earlier with available spare. And then there's media and data integrity errors. And that contains the number of occurrences where the SSD detected an uncorrectable data integrity error, like uncorrectable ECC, a CRC checksum issue, or there was like an LBA tag mismatch. Let's see if this works. Please go to the next slide. So regarding our products, so we have two products that we've talked to you guys about in previous presentations. CM6 is our enterprise class SSD. It's a single dual port. We'll talk about dual port in a minute. For us, we have a 5-year warranty, 2.5 million hour MTBF. Our AFR is 0.35%. We have different power mode settings. And one really cool feature for us is we're on our 6th generation of die failure recovery and double parity protection. And I'll talk about that in 2 slides down. Okay, CD6 is our data center SSD, also value server, entry-level NVMe with power loss protection, et cetera. Also die failure recovery, double parity protection, same warranty, MTBF and AFR. And then lastly, for us on the failure mitigation side, these are Kioxia features. And some of these features may be available in other products in the market, but I'm talking to mine. We support features to protect the drive from failing prematurely and protecting the data on the drive from further corruption. So we have wear leveling algorithms that essentially the wear leveling algorithms are always on. And we're making sure that as let's say that you're hitting a range of LBAs consistently, we're going to make sure that you don't prematurely wear out this section of the SSD. So we're going to make sure that all the NAND is worn equally so that you don't end up with a drive that you basically burned a hole out of. We support endurance throttling. It's disabled by default, but the drive would manage through a credit system how frequently it's written to make sure it meets the 5-year warranty period. And that's with throttling the rights to media itself. We have end of life behavior where we're going to continue to support read and write operations before it meets a critical endurance state. And we're going to inform the host of the different smart flags that are settable that the drive needs to be replaced. And lastly, to me, is our coolest feature. And again, 6th generation, we've had this since our 1st generation SAS SSD. We use an internal RAID 6 architecture to ensure that if a die within the NAND fails, we're able to recover without loss of drive functionality. So the drive doesn't go into read-only mode or failure mode and you've lost all your data. One of the other cool features, which doesn't, to me, get enough press is, dual port drives. This allows for redundancy or high availability usage. CM6 itself will operate in single or dual port mode depending on if the dual port enable pin is set. And dual port allows 2 paths to the same drive, otherwise known as redundancy, right? So if one path goes down, so if you have 2 servers talking to the same drive, and one of those servers goes down, you still have a path to the data that's on the drive. The data is still accessible through the other path. So that's what I brought today. Let me go ahead and turn it over to John Michael.
All right.
Let me see if I can.
Good morning, guys.
That for you.
All right, Mike, you're going to give me control?
You should have control right now.
Yeah, this is going to be better than the last time we tried this and it crashed Zoom. Hopefully the new Zoom update is much better. So, hey, good morning, guys. This is John Michael. I'm a strategic planner and product manager here at Intel. We actually, it's funny, we came back in March of 2020, we did a webcast on the blast radius of SSDs. And actually that was really good to think through that. Actually, since doing that webcast, I actually talked to a lot of experts, at Intel and other companies on disaggregated storage and cloud applications and design, about durability and availability and, this blast radius problem. It's funny, I got a very diverse set of answers on, this blast radius. I kind of mentioned, in that last webcast is, a lot of, if you're a single company and you have one server, then your blast radius is the server. If you are, AWS, your blast radius is, the data center and availability zones across different, geographic locations. You have to worry about different things to guarantee a certain amount of durability. And that's really the right question to ask. I don't know if you guys got a chance to see the AWS reInvent conference. It was actually free this year. You can just sign up and watch the videos. But Peter DeSantis gave a very good talk about AWS's infrastructure, and I thought he had this really cool graph, and it kind of explained, the blast radius increases as the complexity increases, and it gets worse. This Peter's sleep quality, insomnia, as you kind of increase that blast radius size and expensiveness and complexity. But basically, they gave the example of how they, took complicated UPSs and switch gears and, changed them to, batteries, within the rack to basically solve some of this blast radius problem. But this is exactly how we think about the SSD blast radius. So the SSD, if you look back at that, slide before, this is just one part of the entire blast radius problem. And as you look at that graph, as the size of the SSD gets bigger, then theoretically your blast radius problem gets worse, because every single when the drive fails, it's technically more expensive and bigger. But I'm going to explain a little bit about some of our QLC and some of the new products that we have to kind of alleviate some of these concerns. And I think hopefully you'll walk away today thinking that it's actually not as big of a problem as people may think. So if you guys saw in December, we actually launched some of our new PCIe Gen 4 drives on our 144 layer TLC and QLC. And the one I'm going to talk today about is the QLC. So we had been shipping our PCIe Gen 4 product family since the first half of 2020 on the P5500. And the one that I talked a lot about, and if you guys want to go to the Intel Storage and Memory Moment on intel.com, you can watch the whole presentation that I give on this new product, this D5 P5316. But this is really exciting. So we actually are now have potentially launched the biggest NVMe drive in the industry, up to 30 terabytes. And this is a huge gen over gen improvement over the previous gen QLC. So one of the things we mentioned was that at the actual NAND component level, we've increased the write performance by 40%. So your sequential bandwidth on QLC on these bigger drives is actually not a huge bottleneck as it was before. You're in over 3 gigabytes per second sequential write. So if you remember on the blast radius on a single server or single application is basically a function of how fast the drive can write. So if you have, a 30 terabyte drive and you can write at 3 gigabytes a second, it's very easy math to figure out theoretically what the best rebuild time is on a complete drive failure. One of the other things we've done is doubled the endurance on the actual PE cycles, and it's 4 times higher petabytes written compared to the 15 terabyte drive in the previous generation. So this is a huge improvement. And once you get to these large capacities drives, 18 petabytes written random, and we're over 100 petabytes written of sequential endurance, endurance just becomes, far less concern, for actually wearing out these drives on big drives. So I think that was one of these big problems that people had thought about with these big capacity QLCs. And, it's just not something we're seeing in the applications and workloads that we're, kind of guiding people to on QLC. The other thing I talked about, again, if you want to check out that video, I go into very deep detail on some of the TCO models, which is actually interesting. We actually are going to be open sourcing the TCO model that I use for this and for some of the evaluations at Intel that we've done. I'm going to be open sourcing that to SNIA here in the near future. So if you're a SNIA member, you can probably already see it. But I had this, I basically made up this, make-believe configuration. I just picked the biggest super micro server I could find with hard drives, and 18 terabyte hard drives is the biggest hard drive you can buy on the market today. And, I use actually a much better price than you can actually, I think I use 1.5 cents per gigabyte in the model, which, as many of you who have ever bought an 18 terabyte hard drive know that's, they're going for, much more than that today. And then I compared that versus a 30 terabyte NVMe and a 1 petabyte per 1U. And then I pulled this graph out, which was, okay, if you have a TCO dollar per terabyte effective per rack, which is basically, amortizing everything in the rack. So not just, the servers, but all the hardware, the equipment, the networking equipment, the cables, the actual rack itself. And then you're actually adding up all the operational expenses. So the power and rack space and cooling and all that stuff. On an apples to apples basis, with triple replication, you're still a lot higher than a hard drive, right? And that makes sense because NVMe drives are still about 10 times more expensive than hard drives, anywhere between 5 and 10. But the magic is really when you start taking advantage of that flash performance and using stuff like erasure code and compression and things that hard drives can't do in real time. And that actually gets you to this lower TCO. And when I showed this slide, there was a lot of people saying, okay, well, that's great, but you can do erasure code on hard drives. And I'm going to explain, why in Ceph or some other applications that's not very practical. And so there was this thought about these big drives and blast radius being a problem. I actually talked to quite a few people in the Ceph community, and I think I mentioned this before, talking to Red Hat, I think that the limit today in Ceph is 10 terabytes for hard drives. And you have to get like a waiver or like a signed thing in Ceph, if you're using 12 terabyte hard drives, because the rebuild time on triple replication for hard drives is so bad. And they just don't want people to have, many failures. And so they actually limit the actual size, of what is recommended for Ceph configs. But, today talking to many of the experts, it's very common to say that triple replication is actually the default in Ceph. So I had this hypothesis that said, okay, well, if you use erasure code on SSDs, your performance and rebuild time should still be better than hard drives. And your performance is going to be quite a bit more, obviously, because it's flash. And if you add in stuff like compression, you actually have a lower TCO than hard drives, in something like a cloud object store. So I actually worked with our Ceph team at Intel to actually, they've actually done some really cool benchmarking. So they have a 5-node Ceph cluster set up, and then one of them has, they have an Optane cache drive, and then one of them is using 8 terabyte hard drives, and this other comparison is using 15.36 terabyte QLC. These are using the previous gen QLC, but this kind of illustrates the point. And basically, when they did this test with the 5-node cluster, they basically filled it up to 5%. And then they did two things. They yanked one drive and then looked at the rebuild and recovery time of one drive. And then the other test that they did was take down an entire node in the 5-node cluster and look at the rebuild time of the cluster. And this data is pretty outstanding. So looking at triple replication with one drive is actually not bad, 20-minute recovery time with a 5% fill. And you can imagine this scales up if you had 60% of your Ceph cluster filled up, that would probably scale pretty linearly. But when they took the whole node down, it was 3 hours and 45 minutes. And comparing that with twice the actual amount of capacity, so still a 5% fill in the cluster, taking one drive away, the Ceph recovery time was only 3 minutes. And this is pretty wild because this basically, if you do the math on this equates to about 3 gigabytes per second bandwidth. And so this is actually not just a function of the drive speed, right? It's a function of this Ceph cluster happened to have 100 gig networking and lots of fancy stuff in between, so that wasn't a bottleneck. But going back to that blast radius thing, when you think about the blast radius of the drive, there's lots of things that SSD vendors are already doing. Matt mentioned on-die RAID 6. Intel has some on-die XOR that we do that's similar to prevent against die failures on the SSD. But even on the SSDs, when they fail, I think people still have in their heads that these 15 and 30 terabyte drives take, 2 weeks to rebuild. And with SSDs, that's just not the case. There are advanced software applications that can take full advantage of flash performance and flash write speed to actually rebuild these drives faster. As you see, we actually taken an entire node down, and this was, whole node full of 15.36 terabyte QLC drives. The entire recovery time, was only 14 minutes. I mean, that's insanely wild. Now, compare that versus a 4.2 erasure code on hard drives. This was 17-hour rebuild time after losing a node. And this validates the kind of best practices that I mentioned, which was, okay, hard drives and this was with an 8 terabyte hard drive. This, you can imagine 8 terabyte hard drive with a 5% fill took 17 hours to rebuild. You can imagine that this test is actually impossible to run on 100% fill with 18 terabyte hard drives. You cannot run the test. It just would take too long. And that's potentially why this stuff's not in practice. So this was super cool. I can't wait to explore this more. But on the topic, are drives getting too big? Today, hey, we have data that shows with 15.36 terabyte drives today with our old, on our 64 layer QLC, the rebuild times are actually not so bad. And, we imagine as we scale the performance up to PCIe Gen 4 into Gen 5 and increase the drive bandwidth, this is actually just going to continue to improve as long as software is, flash enabled and, capable of taking advantage of the performance to rebuild the flash. And I mentioned all the other bottlenecks, those don't magically go away. That's going to be different, for different applications and different services, whether the network's the bandwidth. Certainly losing a full node of 15.36 terabyte drives is not something you want to do to a network, but there are things built around that you can prevent stuff like that from happening. So with that, I know that was just a snapshot of time of some very interesting stuff, but I know Josh is actually going to walk you through some more software applications that take full advantage of flash performance for types of disaggregated storage. And with that.
Thank you, John Michael. And let's go ahead. Let me give you control, Josh, 1 second. All right, Josh, you should have control.
All right, thanks very much, Mike. Thanks all those out there who are listening today. So let's go ahead and see if we can go forward. And I essentially agree with everything we heard from our other panelists, both from Matt as well as John Michael. We've seen these big drives. Lots of strides have been made to make the individual drives more reliable. And what I want to focus on more is not so much the drive itself, but talking about really how the drives are used in the environment. And what's become, the new normal is to have all these kind of different applications, which all tell you that you should have local flash in every application server. And this starts to touch on something Michael just mentioned, that in that Ceph cluster for centralized storage, everything had 100 gigabit networking interfaces. When they were doing those rebuilds, it certainly sounds like maybe those Ceph nodes were not actually serving a lot of other data, that they had the freedom to completely focus on the rebuild. This is not the case when you go ahead and use local drives on every single application server. They're using the drives themselves. This gives you great performance, good response time. The applications, of course, as kind of mentioned before, have to do their own data protection, usually via triple replication. You get great performance, but you often get very, very poor flash utilization. And on a drive that's 30 terabytes or 60 terabytes coming up, that's a lot of expense for the one time in 100 you need it. If you're provisioning to maximum need, you're going to have a ton of unused space, which is a ton of money that you've wasted. And the recoveries are going to be really long. That's because the application servers, odds are, in a modern infrastructure, are going to have 25 gigabit interfaces. Oh, and by the way, they're trying to do things like actually serve a database. So when they're focusing on a rebuild due to a drive failure or due to a host moving to a different server and using the local drive, you could have a really long degraded impact on your network and the application itself. And of course, everything is tied to servers that have these drives. Estimates vary, but if you actually had a full 30 terabyte drive and you're also trying to run the application at the same time, you only have 25 gigabit networking. The recovery of a 30 terabyte drive could take 8 hours. And that's basically saying that you might get about a realistic 1 gigabyte per second recovery rate because you can't use the full bandwidth because the application is trying to run. The application doing the rebuilding is not necessarily 100% focused on the rebuild. So this can take a really, really long time just using local drives. Secondarily, John Michael touched on the fact that these big drives are enabled with QLC NAND, which is going to be great for making them less expensive to get to these really large sizes. And to do this, though, generally, you have to write to the drives to get the good endurance. And I think someone in the chat also touched on this, posting a message that if you use existing methods like local Linux RAID, things that are doing read, modify, writes to drives, in this case, really flash drives, they're going to kill the endurance of QLC drives. If you try to write all the time in 4K blocks to a QLC drive, you'll just hammer the endurance. If you write to it in very large blocks, it depends on the drive technology. It could be a 16K indirect, it could be 32. Future ones may be as big as 64. But if you write in these large blocks and you write sequentially, you can actually extend the life of the drive or extend the endurance by up to 5 times. So this means when you're going to put one of these large drives in an application server, you have to think, do you have total control over how that application is writing to the drive? Or the file system, if you put a local file system on, do you have control? And odds are your answer is going to be no. So in theory, you might have to completely modify your application. And that's just not an option for most folks. I mentioned your local software RAID is just simply not optimized for QLC. It'll end up killing the drives. And look at the performance you get on the drives too. A lot of these QLC drives can do 500K IOPS or more in reads per drive, but you look at their write performance, and it's only 11K IOPS when you do random. But if you do large sequential writes, and these are right off the data sheets, in this case of one of the Intel drives, if you do large sequential writes, you get 1600 megabytes per second versus 44 megabytes per second of bandwidth. So look at the huge impact that writing sequentially has, not only on endurance, but on the performance of the drive. I touched on this, so just to tell you to think about the fact that we very commonly see 15 to 25% utilization of flash when it's in the local application servers amongst our customers. We have a very large web scaler who reports that they only have 5% utilization. And why, you may ask? Well, because if your operations team says, for simplicity, we're just going to put a drive. We want to make everything the same. So we're going to put flash drives in every single application server. Someone has to pick a size. And if they pick a size that's too big, well, you have a ton of wasted space. If you pick a drive that's too small, it becomes unusable for the applications. So tons and tons of flash is wasted, and you simply don't want that on a 30 or a 64 terabyte drive. So we believe really the answer is LightOS, and John Michael had touched on this, and that LightOS is software-defined storage. It's very high performance. It's local flash performance over standard TCP/IP. It gives you a complete virtualized block layer. It's clustered for high availability and expansion. It offers data services like you're used to in traditional all-flash arrays. All volumes are thin provisioned with inline compression. You can turn on or off. We have space and time-efficient snapshots. And cloning is thin, so you're not using up lots of extra flash. This goes toward what was being talked about the features of flash and the low latency of flash, enabling certain features that you could potentially do on spinning drives, but would be very, very hard to implement or would be very, very slow. We support full multipathing with user-defined failure domains. So addressing that blast radius issue, you can actually deploy over things like multiple racks and make sure that the volumes are spread over different racks. And very, very important here, we have internally in each server with these drives, we protect against drive failures, because no matter how good a drive is, drives are going to fail. It may not even be the drive's fault. It may be the slot. It may be a power connection. It may be a loose connection. It may be the drive carrier. Drives are going to fail. And so when you have that happen, you don't want to rebuild a 30 or a 60 terabyte drive over the network. If you had to, you definitely don't want to just blindly copy everything over, including zeros, because that's going to really impact your network. So we have a feature called Elastic RAID that we protect against drive failures in the server. And I'll touch on that a little more later. And lastly, of course, none of this is good if it doesn't fit into your environment. So we slip very nicely into cloud-native environments with CLI interface, REST API, as well as plugins for CSI, OpenStack via Cinder, and monitoring fits into the systems of your choice with Prometheus and Grafana. So this is a little bit of what it looks like. You see standard servers on the left. You see standard servers full of NVMe on the right. We certainly hope you would consider using the new Intel 800 series Ethernet adapters with 80Q that are going to bring performance down to RDMA type levels. So we're going to get latency down below 100 microseconds for individual reads. But we perform very, very well at scale. At 70% load on our systems, you're going to get under 200 microsecond reads and about 300 microsecond writes. And that's at 70% load, meaning you're getting up into the millions of IOPS for reads and hundreds of thousands of IOPS for writes per target server. We are a clustered solution. So the larger you make your cluster, you get an aggregate performance up into the tens of millions of IOPS and millions of write IOPS, as well as very, very high bandwidth. So NVMe is in the servers that are dedicated to storage on the right. Standard TCP/IP networking. This doesn't need Rocky. It doesn't need special NICs. These are standard Ethernet NICs. Again, going back to though, if you chose the Intel NICs, you would get lower latency with 80Q technology. And you see all your applications run completely unchanged over on the left there. But the difference is while they might be producing a very, very random 4K write load. Once it hits the storage servers are actually sequentializing that. So that's the magic of LightOS. It is actually, it enables QLC flash, because LightOS is always virtualizing all the writes that come into the servers, completing in a non-volatile memory. In this case, it's Intel Optane persistent memory. So we're doing the random writes and random write patterns from multiple hosts into Optane persistent memory in the targets. We protect against write holes and, of course, power failures in this way. Then the data is serialized, and it's always written to the QLC drives, or any flash for that matter, in large blocks and sequentially. So because we're completely virtualized layer, even if we have to do a rebuild, we're only rebuilding data that had actually been written. So we're saving time there. And it's a completely distributed rebuild inside the server. That is, we're not going outside the server for a drive rebuild. So we're not flooding the network. We only rebuild blocks that have been written, and it's a multi-reader, multi-write, because we rebuild into spare capacity, not a single drive. This means that you're reading from all the surviving drives and you're writing to all the surviving drives. So you get a very, very fast rebuild inside the target server without affecting your network. And this really makes us perfectly suited for QLC NAND, because we're always treating the NAND the way you want to write to QLC NAND, and you can use it in areas that you thought you couldn't. And lastly, this actually gets higher performance out of the QLC than you could get if you were writing to the drive directly in 4K random, because we're going to go ahead and spread that load over multiple drives, and we're always going to write to the actual NAND in large block and sequential. So with that, LightOS we feel is really optimized for large SSDs, because you're sharing these SSDs, so you're getting much, much better ROI by making sure you're fully utilizing them. You still get local performance, maximum return on investment. You're going to avoid network saturation issues, especially due to drive failures or due to an application moving from a physical host to a different physical host, because rather than rebuild over that network an unpopulated drive, you're just going to simply use the persistent volume that you had before. If you do have a drive failure, elastic RAID inside the LightOS targets is going to rebuild in an optimized fashion. It's not going to impact your network. And as I said many, many times, so we are using Intel Optane persistent memory to have very, very fast writes, a fast non-volatile write buffer, as well as something I didn't really touch on. When you have these giant drives and you have a lot of them and you're virtualizing out the block infrastructure or the block tables, you need a lot of metadata. And we can also use Optane very nicely here for these large drives because we can support very, very large memory configurations and keep that metadata very close to the CPUs in Optane PMEM. So we're not only using it in a non-volatile way for the write buffer, but then we have regions of that memory allocated in a volatile fashion for the metadata, but the metadata then is very close to the CPUs, ensuring very, very high IOPS and low latency. So that is all I have. Thanks very much.
Thank you, Josh. Let's go to the Q&A session here. All right, so our first panel question, we'll start with Matt, and then we'll go to Josh, and then finally John Michael, and we'll kind of rotate this around. But the first question is, I think we've probably answered this, but I'll let anybody throw in anything else you want to. Blast radius is a growing concern. How do we manage blast radius so servers and applications aren't impacted? I think we probably hit this one, but if you guys want to throw anything more into this, feel free to do so. Maybe a closing statement.
The closing statement. So just, I think the guys touched on it. You know, there's erasure encoding. There's all sorts of things that you can do to manage the blast radius. You know, for us, we've had a 30 terabyte drive that's been shipping for the last 5 or 6 months, a 2.5-inch drive. And, you know, we're working with some erasure encoding guys and some other guys just to figure out what the rebuild times will look like. John Michael touched on it. When you go to PCIe Gen 4, the speed at which you're reading and writing from the drives locally is pretty significant, and that'll basically decrease your rebuild times if you do have a drive failure in the field.
Excellent. Josh, you don't have anything to add from what you've already covered?
If Josh could take himself off mute, he'd answer. No, I think we basically covered that. We believe that you use the large drives, but you mitigate blast radius by go ahead and doing multiple copies over different racks, over different rows, over different power levels. And of course, you spread the data out over multiple drives so that when you do have a drive failure, you have as little impact as possible.
Excellent. And John Michael, we'll let you do the last closing statement on this one.
Yeah, I know I could talk for hours on this topic, but I think, Josh touched on it, which is, the market's efficient. It's going to end up figuring out how to use the thing that's the best total cost of ownership, and that is QLC and NVMe over time, and it's going to beat out hard drives. I truly believe that, and it's after spending lots and lots of time, thinking about this problem with different other applications. And making sure your software is optimized for Flash, especially QLC. Josh touched on all the things you can do, like writing sequentially and having unique rebuild type of architectures that take full advantage of the Flash performance. The network thing is going to be tricky. It's just definitely going to be different for every different kind of application. This is a much different problem in hyperscale than it is, for durable storage. Locally, it's much more challenging in a hyperscale environment than it is for something like, a single box or, a single all flash array. And so these become much larger, bigger scale challenges. But the first principle, which Matt touched on, is just make the drive fail less. And all the SSD vendors are highly focused on that. And we have now, SSDs that are, say 4 to 10 times more reliable than hard drives. And we have technologies in the pipeline that will, continue to improve that about another 2x here in the next couple of years. So we're super excited about all the opportunities.
Very good. Let's go to the first audience survey question. I'll launch that right now. And that question is, to what extent is the SSD blast radius problem an issue for your organization? So there's a few choices here. I'll let everybody go ahead. If you go into the polling window in Zoom, you should see the poll. Go ahead. We'll give you a couple minutes to answer that. And while we do that, we'll go to panel question number 2. And that question is, the terms smart storage and computational storage continue to be ones that are brought up as a solution to this issue. For what types of workloads is this a viable solution? Josh, we'll start with you, then we'll go to John Michael, and then finish up with Matt.
Thanks, Mike. Actually, I want to be abrasive here. I don't see smart storage or computational storage as a solution for this, not at all. I see this as very interesting technologies that can potentially speed up things. I've seen some papers recently on like law firms and things that have to do e-discovery, and they actually have algorithms inside the drives looking for certain terms and whatnot as documents are stored into the drives. But if that drive fails, nothing's going to change the fact that data is lost, and you have a lot of data that's lost just because it has computational or smart storage. If smart storage means that drives actually start maybe talking to each other and doing their own data protection or their own erasure coding, that's interesting, but I don't know of anybody implementing anything like that yet today.
Very, very good points. John Michael, do you have anything to throw in on this one?
Yeah, I think you've seen, stuff like, AWS and Nitro kind of offloading common things, like, compression, encryption, virtualization, and things that are just common storage things you have to do to get the best TCO. And I think that's part of it. We didn't get time to touch on all the cool things that are coming in NVMe. I don't know if they call them, I don't know if, computational storage is really not under that bucket, but stuff like ZNS and zone namespaces, where you are now starting to actually break the SSD up into zones, and you can have, different protection methods, different ECC engines, different erasure coding across different drives and zones across, different collections of drives. There are lots more options for what to do in the future. And, this also allows you to reduce the blast radius from the drive now to single dies and, multiples of zones. So there's lots of cool things in the pipeline. But as Josh alluded to, this is a problem people have to deal with today. And there already are solutions in the market for some of these things that are broadly available. So.
All right. Yeah, and that's a good point. I think if you look at the NVMe spec, the number of new capabilities that's added in for storage, I mean, we have to stop, not just thinking about what the media is, but how we use it. I think there's still a lot of the old hard drive mentality around, and certainly a lot of the NVMe capabilities like zone namespaces get around that. So that's an excellent point. Matt, what do you have to say on this one?
I'd have to agree with both gentlemen. Computational storage, smart storage are very marketing bingo-esque terms today in the market. There are certainly applications for them. I think copy offload and rate offload are pretty popular types of workloads where these types of solutions could be useful. Maybe in the future there'll be inline compression similar to what SandForce had back in the day. Other than that, if you're doing data search and data filtering at the SSD side, you could see some system performance accelerating.
Very good. Let's go to audience survey question number 2. And this question is, when looking at the solution for blast radius problems, which of these approaches has your organization explored? And this is a check all that apply. I'll go ahead and launch that. Again, we'll give a couple minutes for everybody to fill out those answers. And let's go to the third panel question. And that question is, what role can NVMe and NVMe OF play in helping to balance the relationship between SSDs, processing power, data management, and application demands? And Matt, we'll start with you, then we'll go to Intel, not Western Digital, and then we'll finish up with Lightbit. So let's go ahead and take that one.
With NVMe over Fabric, going into those fancy, rocky networks where you have 100 gig, 200 gig Ethernet connections, even 25 gig Ethernet connections. I mean, moving to NVMe over Fabric realizes high performance, low latency. And if you do have systems that are Ethernet attached, the rebuild process, the stranding of devices out in your storage network, that all gets sort of minimized with how quickly you're able to recover from these types of instances. Other than that, anything that you can do to improve system performance by alleviating host CPU load. So if you look at technology, things that are in the NVMe specification, like controller memory buffer or persistent memory region, where you're leveraging the DRAM on the SSDs to help with things like NIC to DMA or DMA to DMA transfers, where you're basically, taking the load off of the CPU and the DRAM and allowing the drives to talk directly to the NICs. That's going to help out with staging, with reads and writes as well.
Excellent. John Michael?
Yeah, I kind of stole the thunder before talking a little bit about zone namespace and some of the other things that are going on. But if it's not clear, if you're developing big drives, NVMe is the way to do it, right? NVMe is now the language of storage. And it's not just, I think there are some perceptions in the industry that NVMe is just for the high performance. But, our lowest cost dollar per gigabyte SSD in the entire roadmap for Intel is NVMe, right? It's QLC. And NVMe is just that is the way that you manage drives. And I mentioned there's lots of stuff coming, like NVMe over Fabrics can help reduce latency and make software more efficient in those multi-node clusters, or for hyperscale data centers. You have stuff like zone namespaces, which are really optimized for large capacity QLC, to reduce over provisioning, reduce costs, make the writing much more efficient for types of QLC flash. There's all kinds of really exciting stuff coming in the pipeline. So just, if you're not involved in NVMe development and monitoring all the new stuff that's going on in the spec, you definitely hop in.
Very good. And Josh, I'll let you finish up this answer.
I feel like I'm cheating because this question was basically just developed for me. Obviously, as an NVMe over Fabric storage solution vendor, we kind of think that NVMe over Fabric plays a large part in NVMe drives for all the things I pointed out earlier. Look, if I have a 60, or I think by next year we'll see even 120, 128 terabyte drives. These things are so massive. It starts to get into the question of how much space do you need even on a local host. And then if you tried to share that on that local host, you start getting into noise neighbor problems. We think disaggregated, composable, software-defined NVMe over Fabric storage on a network that everyone understands. You don't have to learn anything new. It works on TCP/IP, still getting you, as was it talked about earlier, very, very low latencies, down into single transactions in the 100 microsecond ranges, and then for under load, 200, 300 over Fabric. your applications really are not going to know the difference that these drives are not local, and you're going to get all the benefits that we've known basically, since the 90s and the rise of SAN. We used to call it DAS, and then we somehow went into converged instead of calling it DAS, and now we're right back to saying no, you should share, because drives are so big, so much performance, so much capacity. You should share, and NVMe over Fabric is the perfect complement to NVMe drives.
Perfect. Let's go into the Q&A real quickly now. We've got 3 questions. First question, Josh, is for you, and that is Lightbits. Your network adapters are smart NICs or regular?
They are regular. Not to say that's bad. They're just, you use whatever you want. If you want to go ahead and use you could use a 200 gigabit interface, 100 gigabit interface. You could use the Intel 800 series NICs and enable ADQ technology to bring your latency down closer to RDMA type latencies. So you can use any old NIC. You could even use a 1 gigabit NIC if you wanted to, if you had a server, and it will work just fine because we're just on top of standard TCP/IP.
Perfect. Okay, the next question. Does the serialized write to flash apply to power fail scenarios as well? Does that mean that you'll not need so much current from PLP caps? Any more data on that?
I could tell you on Intel drives, our power loss protection is not workload dependent. You can be writing it, full bandwidth, 3+ gigabytes a second, and during an uninterrupted power loss or hot plug, the drive will, correctly write all the data that's been committed to the host in flight to the NAND prior to the PLI caps being discharged. So, yes.
Matt, do you want to comment on that as well? Is that relevant to your drives?
I mean, we have to put enough PLP caps on there to handle anything, as John Michael's saying. I mean, we can't just count on a specific application and then have another customer use the SSD in an entirely different manner and not have enough PLP cap coverage to cover all the writes to flash.
Very good. And our last question is, and this I think had 2 parts. So it looks like one of them disappeared, and then we'll have another question popped in too.
Yeah, I'll go to Ernst directly on these, Mike. Sorry, they're a little bit more about our product planning, so I'll talk to Ernst directly. I reached out to him over
sounds
LinkedIn.
Good. Perfect. And then the last question we have is this is to Josh. As you mentioned 1 gigabit, do you suggest anything less than 25 gigabit? I assume he's talking about network speeds here.
Yeah, the answer is probably going to be one you expected. It depends. Your mileage may vary. It depends on your need. Would I expect anyone to use 1 gigabit? No. 10 will also work just fine, but it's going to be a matter of how many IOPS do you want to be able to get from your client, or how much bandwidth. So naturally, your IOPS and bandwidth are going to be limited by your NIC speed, and also you want the NIC behavior. As the NIC becomes more congested and you start getting, this is TCP/IP, so it's easy. But if you start pushing toward the edge, you're going to get, more retries, timeouts that the system is going to have to deal with. So 25 gigabit is basically what we see most people doing for greenfield deployments. 10 is just fine, and if you want, you could go ahead and bond 2 10s together to get 20, because it's TCP/IP. That just works the way you know how to do LACP or other aggregation protocols. So I hope that answers it. You could use 1, but probably at least 10, and most people for greenfield are using 25.
Perfect. And we have one person who's asking for contact info for the presenter today. I will send you guys his email, and you guys can respond to him appropriately. I think that's all the questions we had for today. So with that, again, this session is being recorded. We'll provide that recording to everybody who registered. That should go out on Thursday along with the PDF of the slide set. And with that, thank you, everybody. Thanks to our panelists, Josh, Matt, and John Michael. Again, it's always a great time to have you guys out here, and looking forward to having another webinar with you guys shortly. Have a great day, everybody.
Thanks, everybody.
Yeah, and
Thanks.
I'm pretty
Take care.
easy to find on LinkedIn if anybody needs to ask me some questions about QLC or SSDs or any other topic. So.
Thanks again, all right. Thanks.
Okay, folks. Bye-bye.